Hello, Psychology 170. As promised, I am recording my lecture. I'm actually in my hotel room here in New Orleans, getting ready for the HFES Healthcare Conference. So let's look back at where we were when we last left off. We were talking about memory, and we had just started talking about sensory memory, talked about that for a few minutes. And in terms of sensory memory, I think the best way to think about it is for your senses, certainly for vision and your auditory sense, you've got a short buffer that records the most previous kind of stimulation that you've received. So if you hear something and you didn't understand it, there's a short period of time, I think echoic memory is something like 5 to 8 seconds even, it's pretty long, where you can repeat things in your mind and sort of have a chance to hear them a second time. You have the same thing for your visual memory, and your visual sensory memory is called iconic memory. And iconic memory is just a couple hundred milliseconds, 100 or 200 milliseconds. And it's the sort of thing where if something's displayed on a screen and then it's turned off, you continue to have a sensory presence for it for a short time, a couple hundred milliseconds. So for instance, if you're in a room and you want to turn off the lights and go jump into bed, you turn off the lights and you've got a split second there where you sort of still see the layout of the room and you can start to navigate through the room. I think I also used the example of you're walking by somebody in a hallway and you kind of glance up at their face right before you walk by them. You can hold on to that image of their face and continue to sort of inspect it and see, oh, hey, was that my friend? Is that somebody I recognize or not? So these sensory memory short buffers give you a second chance to perceive something if you didn't get it the first time. But they're very short, they're very fragile, they decay very quickly, and you can't really hold on to them. The second form of memory is working memory, and working memory is kind of like all the current stuff that you have in mind that you're thinking about. So right now, my working memory is filled with theories of working memory. And I'm trying to think about how to organize what I'm going to say to you so it makes the most sense. So working memory is the kind of current contents of consciousness. You have a very limited capacity. There's only so many things we can keep in mind at once. And we're going to talk in a moment about the format of working memory, because it seems like you have very distinct subsystems in your working memory. You have certain kinds of formats of the information that you can hold. And then finally, there's long-term memory. And long-term memory is much more stable. Long-term memory lasts for years and years, potentially. And you do not need to be actively storing it, as opposed to working memory where you have to actively rehearse things to keep them in your working memory. In long-term memory, they've somehow been what we would say is consolidated into a more stable form so that you can recall things later without having to keep them actively in mind. So let's go back and talk a little bit more about working memory. So the most dominant model of working memory is Baddeley's model of working memory. And it was originally proposed in 1986, and then he updated it in 1990 to add that episodic buffer you see there in the middle. It wasn't in the original model. So first, let me say there's short-term memory and there's working memory. And for the most part, they're pretty much the same thing. Although in the field of cognitive psychology, there's a little bit of a distinction such that short-term memory is kind of like passively encoding stuff where you're just rehearsing things. And working memory has the implication that you're actually manipulating the items in memory. So if you knew, you just met 4 people, Joe, Liz, Sarah, Tiffany, and and I was going to say you need to put their names in alphabetical order. That's typically my example. But actually, I just happened to say Joe, Liz, Sarah, Tiffany. And that is in alphabetical order. So let's say you had to do it in reverse alphabetical order. Or you had to think about their ages. Okay, so let's arrange those 4 people according to their ages. I think the ages from youngest to oldest would be Tiffany, Sarah, Liz, Joe. So that also happens to be reverse alphabetical order. Anyway, the point is I'm manipulating the information. I have those 4 names in my memory, and I'm manipulating something about the order that I have them in or something like that. So that's the idea of working memory. You're actually doing something with the contents of your consciousness, and you're trying to decide things or figure things out or manipulate information. So here we have this kind of rather strange model. I don't know why this kind of Shiva-looking guy with his 6 arms, but this is the central executive portion. So regardless of whatever graphics they chose for this, the idea of a central executive is a system that coordinates the 3 subsystems that compose working memory. So your 3 subsystems are the visual spatial sketchpad, the episodic buffer, and the phonological loop. And I'll talk about each of these 3. But the central executive is sort of the idea that you have a strategy. You understand which of these subsystems you need to use for what tasks, and the central executive is coordinating between these different subsystems to enable your thinking. So let's first talk about the visual spatial sketchpad. This could be something, you could think about this as your current mental imagery or kind of visual or spatial things that you're holding in mind. If you glance at a scene and remember a couple of items from that scene, those items are being held in that visual spatial sketchpad. Another example would be, so for example, imagine that you are out furniture shopping, you look at a desk, and then you think, is this going to fit in my office? I have a certain amount of space between 2 bookshelves, and I can imagine what that space looks like. And then I can look at the desk that I'm looking at in the store, and I can try to make that mental calculation. Is this too big? Is this too small? Would it fit between those 2 bookshelves? Am I going to have to rearrange things? If you're doing that, you're holding mental images in mind, and that's the visual part. And then you also are doing some spatial calculations about the size of these things and the distance between them. So that's the idea of the visual spatial sketchpad. One more example quickly might be if you are thinking about directions. So you're telling your friend how to get directions to your house, and as you tell your friend different things like, okay, I want you to go down, whatever, Central Avenue, turn right on First Street, turn left on Broadway, whatever the streets are, you're calling up mental images, and you're thinking about the location where you need to go to, where you're coming from. You're telling your friend, okay, at the corner of First and Broadway, you're going to see Wells Fargo Bank, turn left at the Wells Fargo Bank. This is the kind of information that you're holding in your visual spatial sketchpad. Let's skip episodic buffer for a second. Let's go to the phonological loop. The phonological loop is the subsystem in your working memory that holds specifically auditory information. So in your phonological loop, this is when you're rehearsing something so that you can just kind of keep it stored, something verbal. So you're going into the store, and your friend says, hey, let's get some mustard, mayonnaise, bread, cheese, and turkey slices. Okay, cool. So mustard, mayonnaise, bread, cheese, turkey slices, etc. You're kind of holding that in your mind, and you might be rehearsing it over and over. So the phonological loop, another classic example, and this is really outdated now, but the classic example is when we used to have phone books, and we would go look things up in a phone book. The phone book might be on the other side of the room. So you want to go order a pizza, you go look up the phone number to your favorite pizza place, and it's 408-924-5547. That's actually my office number. That's not a pizza place, so if you ever called that number. But you say to yourself, okay, 408-924-5547, 408-924-5547, and you're kind of repeating it over and over and over, and that has a way of keeping it active. And by repeating it, that's the loop part. So you repeat things in this phonological loop, and it keeps them active for a short period of time. The phonological part comes from the idea that the contents of this working memory are actually very verbal in their format. So words that take you longer to pronounce out loud will take you longer to rehearse in your phonological loop. And they've done some interesting studies. So if you're holding a bunch of words in your memory, so like let's say I take you in the laboratory and I give you a list of like 10 words, and I say, remember all these 10 words. If the list contains 10 one-syllable words, you're going to have a much better time. You're going to have higher recall of the one-syllable words than you will if the list contains 10 three- or four-syllable words. And the reason is that you have to rehearse things within a certain amount of time or else you lose them. That's the loop part. You kind of rip through all the items you're trying to remember. You go back to the beginning of the list, and then you repeat them again to yourself in your inner phonological loop. So they've discovered that if you have really long words, they take longer to rehearse. So that's the phonological part. It sounds like something in your mind's eye or your mind's ear. You can hear those words as you repeat them to yourself, and longer words take longer to rehearse. And so that's a separate subsystem. That's sort of your verbal linguistic subsystem where you rehearse things in order to maintain them in this phonological loop. And then let's talk about the episodic buffer. This was added later. And the episodic buffer is the portion of your working memory where you decide what things should go in what order, particularly in time. So somebody might tell you a sentence like, Bob and Jane showed up to the party, but Adam was there first. And so you're going to manipulate the temporal order of that. You say, okay, actually, in order, Adam showed up first, then Bob, and then Jane. So that's the idea of the episodic buffer. You can remember things and put them in order. So you use this every time you tell a joke. You have to think about what's the punchline here, and then, okay, what are the elements of the joke that I need to set up for the punchline to be effective? When you're telling a story, you consider what things you're going to tell first, second, third. You begin, you launch into a story and you say, wait, hang on, I need to go back and tell you this other stuff first. And you're thinking about what that other person needs to know in order to understand your story. So you're thinking about the episodes and what order they should go in. If you were a emergency medical services worker, like a paramedic or a firefighter, and you show up to a scene and you're asking people, a car accident or some sort of injury, say what happened. You might be interviewing a lot of witnesses, particularly maybe if you're a police officer, and they're going to tell you a bunch of information, and they're probably going to be freaked out, and it's going to come out in probably not the exact order that it happened. So you're going to have to take in that information and consider it, and then when you write your report, put things into the proper order so that you can report them in the order that they happened. So those are the three subsystems: visual spatial sketchpad, episodic buffer, and phonological loop. And the central executive coordinates between all three of these and helps you to strategize about which subsystem you're putting most of your attention and mental resources into at any given moment. So the central executive is a really important part of this. Think about the idea of driving and using a cell phone. Driving is largely a visual spatial sketchpad task. It's a visual spatial task. It involves your kind of motor coordination of the wheel and pressing the accelerator, but you're looking out at the road and you're making sure you stay between the lines and you're maintaining your spatial awareness of where the cars are around you. So for instance, if you had glanced in a side view mirror and you know there's a car behind you to the left or there's another car like behind you to the right, maybe they're not currently visible, but you store a kind of pointer to those cars in your visual spatial sketchpad, for example. So you know where those cars are. And at the same time, you're talking on the phone. So you're talking on it would have to be a speakerphone here in California now, hands-free. You're talking on a phone, and the person's having a conversation. And so in addition to doing all this visual spatial sketchpad stuff where you're actually actively engaged in driving, you're also maintaining your awareness of what this person's talking about. You're thinking about what they're saying, and imagine they're telling you a story. Okay, so now you're using your episodic buffer to kind of understand the order that events actually happen and to create a mental image of that. Well, those seem like three separate subsystems. So why should it be bad for you to talk on a cell phone while you're driving? Well, the bottleneck is not in the subsystems. The bottleneck is in the central executive. That's why it's difficult, because you've got so much going on. You've basically filled up your visual spatial sketchpad, and with the phone call, you've filled up your phonological loop, and you may have some activity in your episodic buffer, and you have to maintain your resources and move them back and forth and switch between these subsystems. And so there's this big bottleneck in terms of the central executive, in terms of deciding which thing that you're doing and when and maintaining all that information. And that's why it's dangerous, because the central executive, For instance, you may get too absorbed in the phonological loop for a little while, and you may withdraw your attention from the visual spatial sketchpad and forget that there's this car behind you to the left, and then you try to change lanes, and then the car's there, and that creates an accident or a near miss. So this is why we say that talking on cell phones while driving, that's kind of the psychological explanation for why those things interfere with each other, even though there's different subsystems. And notice that like the state of California has said, you can't hold your phone in your hand. You can't even have headphones in. You have to just talk on a speakerphone. And they're saying, oh, okay, good, now fixed. So now it's less dangerous to drive. Well, okay, so maybe there's a little less motor interference because you're not holding a cell phone in your hands, but it doesn't really fix the problem, because this legislature doesn't understand that the bottleneck is not in terms of the physical holding of the phone or the physical use of the earphones. The bottleneck is in the central executive. So that's kind of interesting. And if you look at the research, it turns out that using hand-free cell phones doesn't particularly decrease your interference between those subtasks. It's not that the interference is not in holding the phone in your hands. The interference is what's going on in your mind to coordinate between all of these different sub-activities. So here's some other kind of ideas about working memory. It has a limited capacity. So if I gave you a list of digits to remember, and one at a time, like I show you each digit for 2 seconds, and we went on for a while, in general, people can hold about 7 plus or minus 2 digits that don't have any association. So they have to just be kind of random digits that don't have any association. On the other hand, if you can chunk the information, that is, if you can combine some of it. So like, let's say the first 2 digits, one was 20, the next was 17, and then the next one was, 3, and the next one was 17. You might do something like, oh, 2017, that's like this year, 2017. Okay, now all of a sudden, it's one chunk, 2017, instead of 20 and 17, because you've encoded it as the year. And if the next ones are 3 and 17 and whatever, you can say, oh, okay, that's like March 17th. Okay, cool. So now I've got, or I should have said 16, 3 and 16. Okay, that's like March 16th. So instead of those things taking up 20 and 17, now that's one chunk, 2017. Instead of 3, 16, you could think to yourself, oh, March 16th. And then if you combined all four of those numbers together, you could say, oh, March 16th, 2017. And even more, if you could say, oh, I know an event I'm going to go do on that day, then that now is a single chunk, and we'll consolidate those 4 independent numbers, and they no longer take 4 spots in your working memory. They're just taking 1 because you've chunked them. And we're going to talk about chunking here a little bit more, but that's kind of the idea. If you create an association between some of the elements in your working memory, then that association kind of compresses that information. It's sort of like creating a zip file that you can unpack later. And that compressed information takes up less space in your working memory. Another aspect of working memory is that it only lasts for a certain amount of time. So if you keep things in mind, if you don't rehearse them, then they're just gone. Working memory is a very temporary kind of store. And if you don't rehearse information in your memory, it's gone. And you've probably experienced this if you've been at a party or you met somebody and they tell you their name, and then you move on and you talk about something and you didn't rehearse their name, and next thing you know, it's gone. And then you're in that embarrassing situation where you're trying to figure out how to pretend like you know their name and not actually use their name. That's fascinating, Guy. Another interesting thing about working memory is, and this has to do with the phonological loop, since it's phonological, there's this acoustic component, it's as if you're hearing it in your mind's ear. If you're going to confuse information, it tends to be confused with similar sounding information. If there's no other kind of semantic association, if there's no other meaning association. So if I gave you a bunch of letters to remember, and the first letters contain E, G, B, and E, for instance, you might have a harder time, especially if I added E, G, B, E, C, D, G, on and on, you might get confused because they all sound alike and it would be very easy to confuse them. On the other hand, if I give you E, N, W, X, those have very different sounds, and you're less likely to confuse similar sounding letters than you are to confuse very similar sounding letters. So this is part of the evidence that we have this acoustic format in our working memory, this phonological loop, because you confuse similar sounding words or items. And so that indicates a phonological or acoustic encoding. Another thing about working memory is that it has to be paid attention to. So the things that you're rehearsing require attention. And when you're rehearsing them, your attention has to be on them. And if your attention strays away from them and you don't rehearse them, they have the danger of kind of decaying and leaving working memory because you weren't paying attention to them and you weren't rehearsing them. So working memory is very much tied with attention. And I think, this idea I said at the very beginning that working memory is something like the contents of consciousness, the current stuff you're thinking about. Well, one of the things about consciousness is that whatever you're conscious of, you're paying attention to. So Wickens outlined some guidelines for improving or working with working memory to make sure that you increase performance. And it's coming up. It's going to be April 15th pretty soon. So some of you may be working on your taxes. So let's try to use tax preparation as an example of something that requires a whole lot of working memory. So if you look at IRS form 1040, which is by far the most common form that people do, there's a 1040EZ, there's some other 1040s, but it's something like 100 pages of instructions. If you do it like we used to do in the old days before you had software like TurboTax or TaxAct, you'd go get this instruction booklet that's like a couple hundred, 100 pages long or more, and you'd get your forms, and then you go look up, okay, line 1, what are my instructions for line 1? And then you'd have to go look in the book, and you'd have to read the instructions, and you have to hold those instructions in your working memory, then go back to the forms, and then make sure you're filling things out right. Well, that's a whole lot of working memory load. So a software like TurboTax, it breaks it down and it knows the rules for you. And instead of you having to read all these instructions and then coming up with what you should do, TurboTax does something like it starts out by asking you a bunch of questions. Like, did you buy a house this year? Did you sell a house this year? Did you get married? Did you adopt a child? Those sorts of things. And by asking you these questions, it's much less of a load on your working memory because you don't have to read these instructions. The people at TurboTax have thought about that already, and they've turned it into this interview. And an interview is just a lot less of a working memory load because they just ask you one question at a time. And you can query your long-term memory and go, yes, I did buy a house in 2016 or whatever it is, and then you can answer that question. So provide visual echoes of auditory information. So this is sort of like this is why you write down things if you hear them, so that if you're talking on the phone and somebody's giving you a bunch of instructions or something like that, or giving you a bunch of details, directions to their house or whatnot, it's much better to write things down so that you get them out of your working memory and onto paper. And that's kind of like a visual echo of the kind of things that you're hearing auditorily. So these tax software programs are really good at providing you sort of visual cues where it shows you what part of the tax situation that you're working on. Like I know in TurboTax, for instance, they have this whole thing where it's like, okay, here's all your income. Now we're going to talk about your deductions, and they have a kind of bar on the left with the outline. And it shows you what part of the system you're in, like what part of this whole process you're in. Okay, we're in the third step under deductions. And that can help you maintain your situation awareness. Instead of having to just hold it in memory, you can see it on the side of the outline. And likewise, that outline provides a placeholder for sequential tasks. So if you're just filling out your taxes by hand, you have to remember, I was on line 16, subschedule A, and I have to go do this tax worksheet, and you have to go off to this other thing, and then remember that information and then put it back. So using software, what they'll do is they'll just ask you questions, and then they're in the background, behind the scenes, the tax software is filling out these worksheets and things like that and calculating what needs to get calculated. And it puts it into the proper line for you. So you don't have to hold on to this stuff in your working memory and remember, now where did this information go? I just spent 20 minutes, filling out this sub worksheet, and now I can't remember what I was supposed to do, what that was for. Well, these software are going to provide a better support for that. Okay, chunking. This is the concept I was talking about a few minutes ago when we were talking about 7 plus or minus 2 digits. Chunking is the term, and that really is the term. That's pretty funny. Chunking is the term for grouping items in your working memory so that they take up less space. So the best example I ever heard was in my Introduction to Cognitive Psychology class as an undergraduate student. And I remember this gigantic letter sequence, and letters and numbers. So it was a series of letters and numbers that the professor asked us to hold in our working memory. And let's see if I can do it. The sequence was 1, 4, 9, 2, 8, D, U, Z, 3, 1, 4, 1, 5, 1, 0, 6, 6. So that's pretty impressive that I can remember those 10 numbers and letters. And the question might be, how did I do it? Well, it's because they're chunks. So it's not 1492, it's 1492. So I remember Columbus. And then the number 8, like eating, 8. So Columbus 8. And then DUZ is an old brand of soap. And so DUZ is a soap. So Columbus 8 soap. And then 31415, that's the first few digits of pi, right? 3.1415, 926, whatever it is. So that's Columbus 8 soap pi. And then 1066 is the date of the Battle of Hastings. So Columbus 8 soap pie at the Battle of Hastings is the phrase. And then there's even a further chunk I can do, which is I have this mental image of Columbus in his triangular hat on a battlefield biting into a pie made up out of soap. So I have one visual image, which is like a big mega chunk, and then I unpack that into Columbus 8 soap pie at the Battle of Hastings, and then I unpack and unchunk each one of those. So Columbus 1492, 8, the number 8, soap, DUZ, pie 31415, Battle of Hastings 1066. So that's how I can remember 1492, 8 DUZ, 31415, 1066. And that's an example of chunking. So if you can combine things into a single memory, then they take up less space. They're kind of, like I said, they're kind of like a zip file, and they're compressed in your working memory. So instead of remembering the numbers 4, 0, and 8, you can remember 408 as an area code. And so that helps to minimize your chunking. So the example with the TurboTax and things like that is your Social Security number. So your Social Security number is broken into a set of 3 numbers, then 2, and then 4. And that seems to be a kind of format that's easier for us to remember. So you can just remember like 1, 2, 3, 4, 5, 6, 7, 8, 9. Or whatever your Social Security number is, but it's broke. Instead of remembering each of those different things, what is that, nine numbers, you just have to remember 3 larger numbers, and that seems to make things easier. So minimizing confusability. There's a lot of things in the tax forms where it's like line 15A and line 15B, and then go to worksheet 15. And so, okay, now I got worksheet 15, 15A, 15B. Which one am I supposed to be talking about? And that can create a lot of confusion. So if you were going to create a software interface or anything else like that, you want to use much more distinct placeholders instead of things like 15A and 15B that can be very easily confused. And then another one is avoiding unnecessary zeros and codes to be remembered. So I think maybe our SJSU IDs are kind of a good example. I think a lot of people have, you have a bunch of zeros, like 001, I think is how my SJSU ID starts. So it'd be much easier if I could just remember 1 instead of 001, right? That takes up less working memory. And so this is also why you'll see things in newspaper articles where instead of saying, something cost $14 billion, instead of saying 14000000000, they just say 14B, right? So 14 billion. And so that makes it easier to kind of encode and remember that information. Instead of remembering all those zeros, you just say the word billion or million. That's why we have those words, just because they're a shortcut for our working memory. Okay, so that ends our section on working memory. And now let's talk a bit about long-term memory. And long-term memory is a more permanent kind of storage. In our analogy about the human mind, the working memory is like the RAM, the amount of RAM you have, a lot of memory. And long-term memory is like the size of your hard drive. Things that are stored, files that are stored in your hard drive, you can turn off the computer, come back, turn the computer back on, those files will still be there. And so that's kind of like long-term memory. It's some kind of memories that are not in working memory, they're stored, they're permanent. You can go to sleep, you can come back, and you could recall those memories at a later date. That's what we mean by long-term memory. And one thing about long-term memory is that some items seem to be easier to retrieve than others. So it's probably easier for you to remember the names of the professors you're taking classes from right now than your teacher in the second grade. Because you've had a lot more recent experience with your professors that you're taking now than your teacher in second grade. And some of you may be thinking, oh, I'll never forget Mrs. Cross or whatever, she was my favorite teacher. Okay, think about maybe third grade or fourth grade or fifth grade, if you have some particular memory. But long-term memory seems different memories have different strengths. And as anybody who has studied for a test, and then you get into the test and you're trying to recall that information, you realize that you can't get it. You can't pull it out. And so some things have more strength than others. And in particular, the model of working memory that I subscribe to, the theory of working memory I like the most, specifies that there's a difference between retrieval strength and storage strength. And in brief, the idea is that storage strength, which is how well you know something deep down, that only increases and it never decreases. So once you've learned something, it's in there and you can always have it. But retrieval strength decreases over time. So there may be things that you've learned like a long time ago, that those memories are still in there. You may have just lost the ability to retrieve them very well. And we know this because if you go back and you try to relearn something, you're going to be much faster at relearning something than you are at learning it in the first time. So maybe you learned how to play guitar a long time ago and you haven't done it, and then it's been years and years, and so on a whim, you pick up a guitar and you try to start playing, and it takes you a second to kind of get going, but then all of a sudden, all these abilities come out that you had forgotten about. So they were still stored in your memories. You just had lost the ability to retrieve them because you hadn't been practicing your retrieval strength. And so you had a hard time getting them out. Another example where memories might be well stored but hard to retrieve are when, for instance, people grew up in another country or some other city, and they've left and they haven't been back for a long time, and then they come back to their hometown, and being in the context where they had all these memories from childhood starts to cause a flood of memories to come back. And the reason is that the context that you're in increases your ability to retrieve those memories, and they just come flooding back, and you remember, oh man, I remember growing up here as a kid, and there was this baker over here, we went to the bakery, and they would always give us samples of fresh bread, and it was really fun. And that may be something you haven't thought about in 30 years or 20 years or whatever time it has been. So is it that you had forgotten it? Well, kind of, in the sense that you weren't able to retrieve it, but the memories were still there. So you still had storage strength, but your retrieval strength had gone down because you had left that environment and you were away from all those retrieval cues. So those are examples of high storage strength and low retrieval strength. You can have the opposite. Excuse me. So if you've ever crammed for a test, what happens is you're just trying to shove all this information into your brain right before the test, And you might pull an all-nighter or something, and you're just study, 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 and then you're right before you go into the test, you're like, okay, I got this, I got it, right? I know it, I've got all these things, and they're very accessible to you at that moment. And then you go into the test, and then it turns out you have a hard time getting those things out of your memory. That's because those memories were very high in retrieval strength, but they were very low in storage strength. Because you didn't take enough time to learn them over time, the more you space things out, the more likely they are to get into higher storage strength. And you just kind of did it at the last minute, you didn't have time to build up the storage strength. And you have this kind of illusion of fluency because you had just crammed all these things and they feel like they're really accessible and you know the facts. But really they're just kind of like high, they're in your working memory, more or less. And the retrieval strength is really high. Well, the problem with retrieval strength is retrieval strength goes away. So if you think about something else or you get distracted or anything else, that can cause the retrieval strength to decay rapidly. And then all of a sudden, you can't remember those items because they're not stored very well. I should say that the higher the storage strength of an item, the more it protects the retrieval strength from decaying away. So that's the idea of memory strength. And it has to do with kind of how well you've learned a memory. And I think it's useful to think about your ability to retrieve a memory, which is very limited and decays and needs to be refreshed. That's your retrieval strength, versus your storage strength, which is how well you know something deep down. And that has a lot to do with having practiced it over time so that you can increase the storage strength over time. Another idea is the idea of associations. Basically, one rule about memory is the only way you remember anything is by making an association with something you already know. So this is why, and you probably notice in my teaching style, I'm constantly trying to give you other sorts of associations to help you remember the information that I'm telling you. I'm trying to give you lots of real-world examples and try to say how this relates to your life, because if you can understand how information you're learning in a class relates to your life, that's an association. And that's going to increase your ability to remember that information later. The only way you remember information, that information gets into long-term memory, is if you make an association with something you already know. Right? That's kind of interesting. So the more associations you have with a particular memory, the easier it is to recall that memory. And one reason for that is because maybe one of your associations stops working. If you have other associations, you have multiple routes that you can get to that concept. So you're trying to understand a concept. It'd be useful if you, first of all, studied it at different times and places so that you have those environmental associations to act as retrieval cues. So you can say, oh, okay, right. I remember studying that. I was in the coffee shop, and you can kind of do a mental reinstatement where you remember, okay, what was the coffee shop like? And then try to use that environmental cue as an association to recall that information. And then you say, oh, okay, that was chapter 2. I studied that when I was in the coffee shop. And then, okay, chapter 3, I was in the library when I studied that. And then you can think back to, okay, what was it like in the library? What, that kind of thing. Those are associations. The other thing is making associations not just between your environment and when you encoded things, but also between the facts themselves. So the more you can relate, for instance, the things you're learning in this human factors class to other classes you've had. So maybe you've taken cognitive psychology, or maybe you've taken introductory psychology, things like that. If you can relate the things I'm talking about here to those other concepts, you're going to be more likely to remember them. And then finally, we've got forgetting. And forgetting is just the inability to access information that you may have stored. And it seems to mostly be just, if you had to predict whether you forgot something or not, the number one predictor is just how long it's been since you tried to remember it. So the longer the time, the less likely you can remember something. So here, wait, let's see. Okay, so down here we have this graph, and you have your retention, how much of it you remember. And you can see, like, when you first learn something, the forgetting curve is very steep. So this is why when you're cramming, you forget something, or you learn something, and just like the night before a test, the forgetting curve is very steep. You'll forget it very quickly. But the more times you learn something, so here's that first curve, first learned, and then you're forgetting a bunch, then you go back and you study again. and then you get up to 100%. Okay, now the curve is a little shallower, and the drop off is a little less. Then you study again. All right. Then now it's even shallower. Then you study again, and that's even shallower. So this is why all your professors are telling you got to study as you go. You got to study along the way. This is in fact why I'm giving you quizzes at the end of every chapter, because it acts as kind of a prompt for you to kind of encode that information and to rehearse it. And the notion is that we want you to remember this information for the rest of your life. That's why you're going to college. You're paying all this money so that you can have all this information for the rest of your life. So when we have you take tests and take quizzes and things like this, they're prompts for you to review and re-encode that information, and that's going to protect that information against forgetting. Okay, so a little bit more about long-term memory. Long-term memory is just not one kind of monolithic thing. In fact, there's lots and lots of types of long-term memory. And we're going to talk about a couple of different sub-distinctions within long-term memory. The first major distinction is between implicit and explicit memory. Sometimes implicit memories are called non-declarative memories because they're the kinds of memories that are hard to verbalize, that are hard to say out loud. So for instance, if you play a musical instrument or something like that, I'm not very good musically, but I have friends who play guitar or something like that, and they might hear a song and start playing along with it, and then somebody's like, oh, cool, that sounds great. Like, what chord is that, or what key is that in? And they have to kind of stop and look at their hands and think, oh, okay, that's a G. That's in the scale of G. And that's because it's like their motor functioning knew what they were doing, but they weren't able to sort of verbalize it out loud. So when you're really good at something, like performing a motor skill, riding a bicycle, driving a car, that sort of thing, it's not the kind of thing that you normally verbalize. They're kind of like muscle memories or motor memories. And so one example of that is procedural memory. So procedural memory is all the things I was just talking about: how to play a musical instrument, how to ride a bicycle, how to drive a car. These are all procedural memories. How to swing a golf club, how to swing a bat. And you learn how to do these things over time, and you practice them, and then you become fluid at them. But you don't usually think about, if you had to describe exactly step by step how you do something, that turns out to be difficult, because the format of these memories is that they're kind of non-declarative. Another version of non-declarative memories are priming. So priming is when, if you've thought about something once, it's easier to think about it again. So this is also why you study and review right before you take a test. You kind of look through all the information, and that primes those concepts, that makes those concepts active. And they might fall out of your working memory, but if you go back and try to retrieve them later, priming is kind of an increase in retrieval strength. It allows you to go and grab things more easily and quickly. So some examples of priming are, for instance, let's say you're a doctor and you're trying to diagnose patients who come through, and you happen to have a patient with a very rare diagnosis. What can happen is you can start to think that diagnosis is very active in your mind, and you might be more likely to make that diagnosis again because you were very familiar with those criteria, the diagnostic criteria for that diagnosis. And sometimes that's good, sometimes that's bad. So it's good if you catch these rare things if they're coming up, but it's bad if you start to get too quickly, because you've thought about a certain diagnosis, that diagnosis comes too quickly to mind, and you don't think about alternative diagnoses. That would be a downside to priming. Another example of priming is advertising. Why do we have ads all over the place? Well, if Coca-Cola puts that red and white logo everywhere that you look, then the reason they're spending all that money to put that logo and to have those ads in front of you is that every time you see that, you recall the concept of Coca-Cola. So next time you're thirsty and you're thinking, I want something kind of sweet and bubbly, they have paid all this money to put their logo in front of you so that when you go reach for, like, what do I want? hopefully they're hoping that Coca-Cola is more primed and it more easily comes to mind than, Pepsi or RC Cola or Dr. Pepper or any of the other things you could drink. So that's why we have advertising, because they want to just try to kind of boost a thought of a brand in your mind, and that is a form of priming, so that later on you think you're just thinking about things naturally, but the concepts that are most primed come to mind easiest. So those are forms of implicit memories, because you can't really verbally state out loud, oh, my concept of Coca-Cola is 30% primed and my concept of Pepsi is 20% primed, and therefore I will have Coca-Cola come more easily to mind. It's not the kind of thing you have that sort of insight about. Another form, okay, so now let's talk about explicit memory, or what we would call declarative memory. These are things that you can say out loud, very easy to verbalize. And there's at least two major types of explicit memory: semantic and episodic. You can also think about structural memory, how ideas are related. But semantic and episodic memories, semantic is knowledge, facts and knowledge that are sort of independently known, that don't have a time and place associated with them. And episodic memories are memories that have a time and place associated with them. So, for example, what did you eat for lunch yesterday? You can think back and remember what you ate for lunch. That is an episodic memory. And because you know what you did at what time in the certain location, that's an episodic. You remember the episode, right? That's why we call it that, episodic memory. Whereas semantic memory is your memory for facts and figures. So for instance, you might know that Paris is the capital of France, or Sacramento is the capital of California. But do you remember the day and time in school where you learned those facts? You don't really remember like when you learned that Paris was the capital of France, but you know that information. So that's the idea of semantic information. It's more like knowing without remembering. You know that information, but you don't remember when and where you learned it. But in both cases, with either semantic or episodic memories, you can state out loud what they're like and what those facts are, or what those episodes were in your life. So here is a nice chart that's filling out at least the LTM, long-term memory side of things. And it shows you that you've got long-term memory, and it's split into explicit and implicit, or declarative and non-declarative is kind of the other way to think about it. And declarative long-term memory is made up of episodic memories and semantic memories. And your implicit or non-declarative side is made up of priming and procedural or motor memories. And then, by the way, if you looked over here on the short-term memory side of things, you should be able to put in Baddeley's model of working memory. So short-term memory or working memory is composed of your central executive and then your three subsystems, the visual spatial sketch pad, the phonological loop, and the episodic buffer. So one tip for studying for tests and things like this in this class is make sure you understand this whole family tree of memory, all the different subcomponents and how they're different from each other, and what classification, where they go within this. Okay, so for the rest of this course, we're going to talk, rest of this lecture, we're going to talk a little bit about the idea that people have certain concepts, and how you might elicit or find out what those concepts are. So one notion that's popular is the idea of a mental model. And a mental model is sort of like how you think about something, what structure you use. And they're similar to the idea of schemas, if you've heard of that from like a cognitive psychology or introductory psychology class. And a schema is kind of like, or a mental model is kind of like a structured memory representation that has default pieces of information you want to fill in, and they're kind of already auto-filled with certain assumptions. So for instance, I've done some work looking at doctors who hand off patients from one doctor to another. So we did research in a pediatric hospital with pediatric hospitalists, pediatric doctors, and we asked a bunch of doctors what information they thought was really the most useful information to know if they were receiving a patient handoff. So one doctor's leaving at the end of their shift, and then the patient's still in the hospital, so they have to hand off all their patients to the next doctor coming on shift. And they need to tell that next doctor, okay, listen, the kid in room 1, this is a bronchiolitis patient. They've had this treatments. We've sent out for these labs and tests. Here's the next things you need to do. Here's their medical history. Here's their, for instance, their diagnosis, their allergies. Here's what the feeding and the diet is supposed to be for this patient, and on, right? There's all these categories of information you need to hand off. And so what we were interested in is trying to elicit what is the kind of average mental model that doctors seem to have about their patients, so that you can understand it, and so that you could create a handoff protocol that matches their mental models, so that you can improve the way that doctors kind of transfer ideas from one person to another by breaking things into the ways that they naturally think about them in terms of their mental model. When you're talking about mental models, it's useful for that concept of structural knowledge. All right, so structural knowledge, we said, was one of the explicit forms of memory. So there's episodic, semantic, and then now we're talking about the structural knowledge part. So you might ask, for instance, how accurately. So let's take the example of the patient handoffs. Okay, so we actually did a simulation study like this. We created fake patients. We had doctors receive a handoff of those patients, perform tests and things like that, get lab results back, update their diagnosis, and then they simulated handing off that patient to the next person. So one of the questions we asked in that study was, how accurately did they remember the information? So if I told you that this patient had certain medical allergies, and you received that information, and then you did your simulated shift, and then you handed off the information, did you accurately hand off the same medical allergies, right? Like, don't give this kid penicillin or whatever it is. We can also ask about the richness of a person's knowledge. So for each of these categories, how well have you worked it out? So how much information do you actually know? In the case of the patient handoffs, it might be, okay, you received this patient information, and during your simulated shift, you got test results back. And those test results are going to change. They might update your diagnosis of what's going on with this little kid, and you're going to have a little bit more subtlety in terms of your understanding of the patient's situation. So we could try to elicit that and see how well do you actually understand these different concept categories. Another question we might want to ask is, do two people have similar mental models? Are they thinking about things the same way? And one thing you might do there is, for instance, you can look at the mental models that novices have and experts have. And what you'll find typically is that experts have more accurate mental models to what the current situation is, and that novices tend to encode all kinds of kind of extraneous and unimportant information that they don't really understand what's important and what's not to include in their mental model. So that's one example where you could compare novices and experts and see how their mental models are similar or different. But in general, you might want to see, do two people share the same kinds of mental models? Does Dr. 1 have a mental model of patient information that's the same or different than Dr. 2? And so that's a question you might ask. And here's another one. So how about technology? Is it compatible with the human's mental model? And maybe the easiest thing to talk about here is in any kind of software interface, hey, I just happen to have, okay. These are arranged with certain categories: file, edit, insert, slide, format, arrange, etc. And so file, that has everything to do with files. So I can create a new file, I can open a file, I can open recent files, I can close, save, all right? So at some point, some UI researcher had to think about all the functions that you're going to do in this program. And then they had to think about, okay, well, what are the names for all the pull-down menus? And what function should I put under which pull-down menu? And how are humans going to conceptualize all of these functions? How would they group them together? And if you have a software interface that is good, it's going to have a pull-down structure for the menus that is going to be very well understood and reflects people's natural mental models. If you have software that's bad, it's like you're trying to do something in the software program and you cannot figure out which menu it's in. And you keep looking around, and then you find out like, oh my God, why would they put that under this other menu? This seems crazy. Why, that doesn't make any sense to me. Well, that's a software that doesn't have a really good relationship in terms of the menu structure with your mental model as a user. So one of the things you're going to want to do if you're going to be designing interfaces or designing software is you want to make sure you elicit the mental models of your user base so that you can properly organize how your software is laid out so that it's going to match their mental model. So how might you elicit the mental model from somebody? So if you're going to interview doctors and figure out what their mental model is for a patient, or if you want to design an interface, how are you going to do your menus and things like that? Well, we're going to go through right now. We're going to go through several different ways that you can do kind of elicit people's mental models. Okay, so the next section that we're going to talk about, the last part of this lecture, is what are the tools you can use to elicit mental models from people. Well, one is you can have people create a mental, like they can actually draw out their idea of a mental model. They're called a concept map. Sometimes people call it a mind map. And there's actually really good software you can find. I think there's even free add-ons for like Google Docs so that you can create mental models and things like that. And this is actually very, very useful if you ever want to do this for studying. This is a very good way to study. So what you do is you kind of lay out all the information. So this person here is studying something about electricity or energy. They're saying, okay, electricity is a form of energy and then can exist in the form of lightning and things like that. And they say, okay, the sources for electricity, we have mechanical motion, chemical energy, solar energy, and so et cetera, right? So you're just kind of laying out all of the concepts and how they're related to each other. And there ends up being a structure here. You see that there's, electricity is a form of energy, and that could be in the form of, all this other sort of stuff. So one way you can elicit somebody's mental model is you can give them either a blank piece of paper or a software program and just say, listen, just fill it out, right? Like kind of just work on this and fill out your idea of your concept map or your mind map on this particular topic. And then you could look at two different people's concept maps and you can see if the propositions that they came up with are similar. Right? So is there some similarity? Maybe I do not just 2, 3, 4, 5, 6, 10 people that are experts in their field. And I ask them to each fill out a concept map. And then I look at the structural similarities and differences and see if, oh, you know what? They all seem to have this thing right here. They all have an idea of sources, and then they identify the different sources like mechanical, chemical, solar, and maybe somebody else. I guess mechanical would be created by wind, for instance, something like that. So that's our first idea, is you have people draw out their concept map. The next idea for eliciting a mental model is the idea of card sorting. And card sorting is a really great tool for getting at how people organize information. And it goes something like this. You just, in the old days, you would actually write these things on 3x5 cards, index cards like I've got pictured here. You can do that still. It's actually perfectly valid, but there are also software programs that you can use. So what you might do is just come up with a whole bunch of individual items that people are to remember or elements that you want to have. So for instance, if you're designing a software user interface, save a file. Another one would be like duplicate a file, right? And then there's also going to be like show the fonts. And then every little item here, right? Like inspector, format, animate, document, blah, 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 blah. You'll write each of those down on a structure to them. And then you give them to somebody who's a user or whatever. And you say, okay, just combine these cards, put them into piles of things that seem related to you. Okay, so sort these cards however you want. And then you look at a bunch of different people and you see if they sorted them similarly. So for example, let's imagine this with like a deck of cards, okay? So I give you a deck of cards. I say, here's a bunch of cards. They're all random. I just kind of spread them on a table. And I say, just group these into stacks according to something that makes sense to you. So for instance, they might put all the hearts together, all the spades together, all the clubs together, and all the diamonds together. That's one form. They sorted it by suit. Another one might be they put all of the lower number cards together, like 2 through 10, and then they put all the face cards together, right? So that's 2 piles. Okay, this person thought, they think of cards in terms of 2 piles. Another person might put all the 2s together from 4 different suits, all the 3s together from 4 different suits, right? So then that person's got a different mental organization. They think in terms of the numbers of the cards. They put all the kings together, queens, jacks. So the same cards can be organized differently if you're thinking about a deck of cards. And how people do it sort of reveals something about the way that they mentally organize that information. So in the experiment I talked to about with the patient handoffs, we had a bunch of pieces of information you might need to know, like medical history, allergies, medications, tests, results, labs, et cetera. And we just gave them, and then we recruited a bunch of pediatric hospitalists, and we had them do this card sort. So they organized them. And on average, they put 10 different categories. Their categories were history, let's see, I can't remember all 10, but it's like history, allergies, labs and tests, to do on the upcoming shift, and et cetera. And so there emerged among these 10 or 15 doctors like some pretty common categories that they always seem to sort the cards, like they put certain things together. If you're doing a software interface, you would notice, oh, do people organize all file functions in the same pile? Okay, well, I'll make a file menu, right? So you have the individual cards, and then you see what's on average in a pile, and then you have to come up with a name for that pile. And that's what that category, that's what that concept is. Another way you can elicit a mental model is you can take those individual concepts, and then what you can do is you take each pair of those concepts, 2 by 2 or two at a time, and you say, rate how similar you think these 2 concepts are, right? Like super similar, very high, or very low. Like imagine like a Likert scale or something. Like on a scale of 1 to 10, how similar? 10 is very similar, 1 is completely different. And you just do that for every pair, okay? And you do that for a bunch of people. And then what you can do is you can figure out the average distance between concepts. And concepts that have the closest distance end up getting linked together by lines that are shorter. And concepts that have farther distance end up farther away from each other. And so this is kind of a kind of piecewise way of eliciting a mental model, where you look concept by concept. How are people thinking about the similarity between all these different concepts? And it's very difficult to do the mathematics for this, so there's something called a Pathfinder program. And so the Pathfinder program, you enter all the elements, then you enter sort of a grid for every element, how similar is it to every other element, and then the Pathfinder program crunches those numbers and it draws you a concept map. So there's your mental model, there's your concept map. You can use those different procedures, concept maps, card sorts, pathfinders, and they all tell us, for instance, you could get a bunch of experts, so people who are really good in the field, subject matter expert, and you could find out what their concept map is, and then you could look at what a novice's concept map is. And that might tell you sort of the accuracy. So I have a really experienced software designer, how they conceptualize menu structures, versus somebody who just got out of college as a computer science major. Maybe they're brand new to the field and they conceptualize the concept map. They would come up with a different menu structure. You can also look at the richness of a person's knowledge. So particularly if you allow them to just draw out, do a concept map where they draw it out themselves, you can see how many nodes and subnodes and how many relations do they have. Another thing you can do is you can have different people do it. And this is kind of like the accuracy thing, but just 2 different people, maybe the same level, and you see, do they have the same or different concept maps? So that would be a way to find out, like, maybe you're having an argument or something because you guys are thinking about something, you have 2 different mental models for how this thing should go. So that can be a way to figure things out.
And then finally, whether technology is compatible with the human's mental model. I think that's really good, and that fits with all those ideas of like creating a software interface and having your menu structure that matches people's mental models. So here's some guidelines, right? We want to have some prescriptive information after telling you all this stuff about cognitive psychology in terms of human factors. So if you want to have you want to have people regularly use information to maintain the frequency and recency. So you want to keep kind of having them to have distributed practice so that increases long-term memory. Again, this is why I'm having you have quizzes and things like this in this class. I'm trying to encourage your long-term memory. You want to have people to actually try to say out loud the information that they're trying to remember. This is why when you study with another person, it's very, very useful because you can you explain concepts to each other. And by actually explaining something out loud and telling somebody how something works, teaching something is one of the best ways to learn something because it forces you to verbalize out loud the concepts that you're talking about. So you want to standardize to support one common mental model. So certainly in terms of like software development, menu structure, you want to have one particular mental model. Hopefully it's the most optimal mental model. You want to use all kinds of memory aids so that you can put information in the world instead of in your head. So in the field of medicine, this is the idea of checklists to make sure that you have a whole bunch of standardized procedures, checklists that you can go down to make sure that you're doing everything. You don't have to remember it. You just follow the checklist. They also use checklists in aviation. So when a pilot's landing a plane, there's a checklist. When the pilot's taking off, there's a checklist, etc. And having these kinds of checklists, that's a memory aid. You don't have to remember all the steps that you need to do for an airplane landing. You just look at the checklist and you follow it step by step. And so another idea, and when we get into software interfaces, this is going to be an important concept, the idea of transparency. So if you're using some system, you want to make sure you understand what that system's doing all the time so that you can have your accurate mental model. So this is why software programs, they give you things like loading bars, and they say, hey, loading, 5%, 10%, and they're giving you feedback so you don't get frustrated. So you understand, what the state of the system is, and it doesn't get you upset. So that's the idea of transparency, is to make sure that the computer is saying, okay, gathering information, and it kind of gives you feedback about what you're doing. Okay, so I said rehearsal leads to better recall. So on your own, and we can talk about this in the next class, we'll maybe start off with this. So I want you to think, name one thing brains and machines have in common. Name at least one technique to determine whether two people have the same mental model, same structural knowledge. We went over 3 different techniques, so be able to explain at least one of them. Ideally, you can explain all 3, right? And what are some of the things that, what are some of the things designers should do to make sure that their software design is, or whatever they're designing, is compatible with people's working memory. All right, that's it for this lecture. The link. Hope everybody's having a great weekend, and I will see you on, this class is Tuesday, Thursday. I will see you Thursday. All right.